very good morning, students. Today in oceanography, we'll be learning about ocean waves. Waves are among the most familiar features in the ocean. All waves work similarly, so although we are talking about the ocean waves here, the same information would apply to any other waves you might discuss in the science classes. Ocean waves transport energy over vast distances, although the water itself does not move except up and down. This may surprise you, but if you think about it, once you are past the breakers on your raft, you pretty much just bob up and down. After going through this lesson, you will be able to understand the oceanic waves and their characteristics. Waves generally begin as a distribution of some kind, and the energy of that disturbance gets propagated in the form of the waves. We are most familiar with the kind of the waves that break on the shore or rock a boat at the sea, but there are many other types of the waves that are important to the oceanography. Internal waves. They form at the boundaries of the water masses of different densities, that is at the Pycno line, and propagate at depth. These generally move slowly than the surface waves and can be much larger with heights exceeding hundreds of meters. However, the height of the deep wave would be unnoticeable at the surface. Tidal waves. These are due to the movement of the tides. What we think of tides are basically enormous long waves with a wavelength that may span half the globe. Tidal waves are not related to tsunamis, so don't confuse the two. Tsunamis are large waves created as a result of the earthquake or other seismic disturbances. They are also called the seismic sea waves. Splash waves. These are formed when something falls into the ocean and creates a splash. Atmospheric waves. They form in the sky at the boundary between the air masses of different densities. These often create ripple effects in the clouds. The ripple pattern is a result of the internal waves in the atmosphere as described in the figure. There are several components to a basic wave, and some of them are still water level, where the water surface would be if there were no waves present at the sea, was completely calm. Crest, it's the highest point of the wave. Trough, it's the lowest point of the wave. Wave height, it is the distance between the crest and the trough. Wavelength, the distance between the two identical points on the successive waves, for example crest to crest or trough to trough. Wave steepness, the ratio of the wave height to the length. If this ratio exceeds 1/7, that is, if the height exceeds 1/7 of the wavelength, the wave gets too steep and will break. There are also a number of terms used to describe the wave motion, and some of the important ones are period. It's the time it takes for two successive crests to pass a given point. Frequency, it's the number of the waves passing a point in a given amount of time, usually expressed as waves per second. This is the inverse of the period. Speed, it describes how fast the wave travels or the distance travelled per unit of time. This is also called celerity, where c is equals to the wavelength into frequency. However, the longer the wavelength, the faster the wave. Waves of the sea. Most ocean waves are generated by the wind. Wind blowing across the water surface creates little disturbances called the capillary waves or ripples that start from the gentle breezes. Capillary waves have a rounded crest with a V-shaped trough and wavelengths less than 1.7 centimeters. These small ripples give the wind something to grip onto to generate larger waves when the wind energy increases, and once the wavelength exceeds 1.7 centimeters, the wave transitions from a capillary wave to a wind wave. As waves are produced, they are opposed by a restoring force that attempts to return to the water to its calm equilibrium condition. The restoring force of the small capillary waves is surface tension, but for larger wind generated waves, gravity becomes the restoring force. There are three important factors determining how much energy is transferred from the wind to the waves, and thus how large the waves will get. The wind speed, the duration of the wind or how long the wind blows continuously over the water, and the distance over which the wind blows across the water in the same direction is also known as the fetch. Increasing any of these three factors increases the energy of the wind waves and therefore the size and speed. But there is an upper limit to how large wind generated waves can get. As wind energy increases, the waves receive more energy and they get both larger and steeper. When the wave height exceeds 1/7 of the wavelength, the wave becomes unstable and collapses, forming white caps. The ocean surface represents an irregular mixture of hundreds of waves of different speeds and sizes, all coming from different directions and interacting with each other. A histogram of the wave heights within this mixture reveals a bell-shaped curve. In addition to the basic statistics, much as mode, most probably the median and the mean, wave heights are also reported in other ways. Marine weather forecasts and ships and buoy data often report significant wave heights, which is the mean height of the largest 1/3 of the waves. Mean wave height is approximately equal to 2/3 of the significant wave height. Finally, there is the minimum height of the highest 10% of the waves, which is the 90th percentile of the wave heights, often expressed as h 1/10. Under strong wind conditions, the ocean surface becomes a chaotic mixture of choppy, white-capped, wind-generated waves. The term sea state describes the size and the extent of the wind-generated waves in a particular area. When the waves are at their maximum size for the existing wind speed, duration and fetch, it is referred to as a fully developed sea. The sea state is often reported on the Beaufort scale ranging from 0 to 12, where 0 means calm, windless and waveless conditions, while Beaufort 12 is a hurricane. A fully developed sea often occurs under stormy conditions where high winds create a chaotic, random pattern of the waves and white caps of various sizes. The waves will propagate outwards from the center of the storm, powered by the strong winds. However, as the storm subsides and the winds weaken, these irregular seas will sort themselves out into more ordered patterns. Recall that the open ocean waves will usually be deep water waves and their speed will be dependent on their wavelength. As the waves move away from the storm center, they sort themselves out based on the speed, with longer wavelength waves traveling faster than the shorter wavelength waves. This means that eventually all the waves in a particular area will be traveling with the same wavelength, creating regular long waves called swell. We experience swell as the slow up and down rocking motion we feel on a boat or with the regular arrival of the waves on the shore. Swell can travel very long distances without losing much energy, so we can observe large swells arriving at the shore even when there is no local wind. The waves were produced by a storm far offshore and were sorted into the swell as they travel towards the coast. Because swell travels such long distances, eventually swells coming from different directions will run into each other, and when they do create interference patterns. The interference pattern is created by adding features of the waves together, and the type of the interference that is created depends on how the waves interact with each other. Constructive interference occurs when the two waves are completely in phase. The crest of one wave lines up exactly with the crest of the other wave, as do the troughs of the two waves. Adding the two crests together creates a crest that is higher than in the either surface waters, and adding to the troughs creates a deeper trough than in the original waves. The result of the constructive interference is therefore to create waves that are larger than the original source waves. In destructive interference, the waves interact completely out of phase, where the crest of one wave aligns with the trough of the other wave. In this case, the crest and the trough cancel each other out, creating a wave that is smaller than either of the surface waves. But most interference by the swells at the sea is mixed interference, which contains a mix of both constructive and destructive interference. The interacting swells do not have the same wavelength, so some points show constructive interference and some points show destructive interference to varying degrees. This results in an irregular pattern of both small and large waves called the surf beat. It is important to point out that these interference patterns are only temporary disturbances and do not affect the properties of the source waves. Moving swells interact and create interference where they meet, but each wave continues on unaffected after the swell pass each other. In the destructive interference, the source waves are out of phase, so they cancel each other out and produce waves that are smaller than the originals. In the mixed interference, constructive and destructive interference occur at various points, creating an irregular wave pattern. About half of the waves in the open sea are less than 2 meter high and only 10 to 15% exceed 6 meters. But the ocean can produce some extremely large waves. The largest wind wave reliably measured at the sea occurred in Pacific Ocean in 1935 and was measured by the Navy tanker, the USS Rampo. Its crew measured a wave of about 34 meters or about 112 feet height. Occasionally, constructive interference will produce waves that are exceptionally large even when all the surrounding waves are of normal height. These random large waves are called the rogue waves. A rogue wave is usually defined as a wave that is at least twice the size of the significant wave height, which is the average height of the highest 1/3 of the waves in the region. It is not uncommon for the rogue waves to reach heights of 20 meters or more. Rogue waves are particularly common off the southeast coast of South Africa, a region referred to as the Wild Coast. Here, Antarctic storm waves move north into the oncoming Agulhas current, and the wave energy gets focused over a narrow area, leading to constructive interference. This area may be responsible for sinking more ships than anywhere else on the earth. On average, about 100 ships are lost every year across the globe, and many of these losses are probably due to the rogue waves. Waves in the Southern Ocean are generally fairly large because of the strong winds and the lack of land masses, which provide winds with a very long fetch, allowing them to blow unimpeded over the ocean for a long distance. Waves on the shore. Most of the waves discussed in the previous section refer to their deep water waves in the open ocean. But what happens when these waves move towards the shore and encounter shallow water? Remember that in the deep water, a wave speed depends on its wavelength, but in the shallow water, wave speed depends on the depth. When the waves approach the shore, they will touch bottom at a depth equal to half of their wavelength. In other words, when the water depth equals the depth of the wave base. At this point, the behavior will begin to be influenced by the bottom. When the wave touches the bottom, friction causes the wave to slow down. As one wave slows down, the one behind it catches up to it, thus decreasing the wavelength. However, the wave still contains the same amount of energy, so while the wavelength decreases, the wave height increases. Eventually, the wave height exceeds 1/7 of the wavelength and wave becomes unstable and forms a breaker. Often breakers will start to curl towards as they break. This is because the bottom of the wave begins to slow down before the top of the wave, as it is the first part to encounter the seafloor. So, the crest of the wave gets ahead of the rest of the wave, but has no water underneath it to support it. There are three main types of the breakers: spilling, plunging and surging. These are related to the steepness of the bottom and how quickly the wave will slow down and its energy will get dissipated. Spilling. Breakers form on the gently sloping or flatter beaches where the energy of the wave is dissipated gradually. The wave slowly increases in its height, then slowly collapses on itself. For surfers, these waves provide a longer ride, but they are less exciting. Plunging breakers form more on the steeply sloped shores where there is a sudden slowing of the wave and the wave gets higher very quickly. The crest outturns the rest of the waves, curls towards and breaks with a sudden loss of the energy. These are the pipeline waves that the surfers seek out. Surging breakers form on the steepest shorelines. The wave energy is compressed very suddenly right at the shoreline and the wave breaks right into the beach. These waves give too short and potentially painful ride to the surfers to enjoy. Wave refraction. Swell can be generated anywhere in the ocean and therefore can arrive at a beach from almost any direction. But if you have ever stood at the shore, you have probably noticed that the waves usually approach the shore somewhat parallel to the coast. This is due to the wave refraction. If a wave front approaches the shore at an angle, the end of the wave front closest to the shore will touch the bottom before the rest of the wave. This will cause the shallower part of the wave to slow down first, while the rest of the wave that is still in the deeper water will continue on at its regular speed. As more and more of the wave front encounters the shallower water and slows down, the wave front refracts and the waves tend to align themselves nearly parallel to the shoreline. They are refracted towards the region of the slower speed. Refraction can also explain why waves tend to be larger off points and headlands and smaller in the base. A wavefront approaching the shore will touch the bottom of the point before it touches bottom in a bay. Once again, the shallower part of the wavefront will slow down and cause the rest of the wavefront to refract towards the slower region. Now, all the initial wave energy is concentrated in a relatively smaller area off the point, creating a large high energy waves in the bay. The refraction has caused the wave fronts to refract away from each other, dispersing the wave energy and leading to calmer water and smaller waves. This makes the large waves of a point break ideal for surfing. While water is calmer in a bay, which is where the people who launch a boat, this difference in the wave energy also explains why there is net erosion on the points while sand and sediments get deposited in the base. Wave energy is spread out in the base, causing smaller waves. Tsunamis. Tsunamis are large waves that are usually the result of seismic activity such as the rising or falling of the seafloor due to the earthquakes. Although volcanic activity in the landslides can also cause tsunamis in the form of splash waves. As the seafloor rises or falls, so does the water column above it, creating waves. Only vertical seismic disturbances cause tsunamis, not the horizontal movements. These vertical seafloor movements are usually less than 10 meter high, so the resulting wave will be of an equal or lesser height at the sea. While the tsunamis have a relatively small height at the point of origin, they have very long wavelengths up to 100 to 200 kilometers. Because of the long wavelength, they behave as shallow water waves throughout the entire ocean. The depth of the ocean is always shallower than the half of their wavelength. As shallow water waves, their speed depends on the water depth, but they can still travel at speeds of over 750 km per hour. Waves are undulations of the surface layers of both large and small bodies of water. They are in fact one of the most obvious phenomena of the ocean. Wave phenomena involves the transmission of the energy and momentum by means of vibratory impulses through the various states of matter. Theoretically, the medium does not move as the energy passes through. The particles that constitute this medium simply move in a back and forth or orbital pattern, transmitting energy from one another. So, in today's lesson, we have learned about waves and their different characteristics and also about tsunamis. So, thank you and have a nice day.